We switch now to English for the next presentator. Please welcome Armin Wisthaler from the University of Oslo. You will have a presentation about volatile organic compounds in Oslo air and their source apportionment. Yes. So please, Armin Wisthaler.
Do you hear me? Yes. Okay. So first of all, thank you very much for the invitation. Thank you, Elisabeth, for thinking of me, for former supervisor. So yes, I'm going to talk about VOCs, but I think also some other work we have done in Oslo. And since it's the first time I speak to this audience, I will introduce myself and my group. So I'm the professor of atmospheric chemistry at the University of Oslo. I'm also an adjunct professor in Innsbruck still. And this is our key research areas. So what we have done a lot in the past years is emission characterization. I will show today some work we do on, still there is some internal combustion engines around, and so we do car emission exhaust. We have done a lot of work in Norway about emissions from carbon capture, CO2 capture. We have done the emission measurements at the pilot plant in Klemetsrud, where you will have the first full-scale CO2 capture plant installed. We have done emission measurements on ships, biogenic emission measurements on jet engines that are powered on biofuels. And this is, well, that's more than 10 years back, emissions from fracking. Then we usually we do very few measurements actually here in Norway. And today I will show some of the measurements we have done here in Norway. We participate in large international field campaigns usually. We have 1-hour instruments flying on NASA research aircraft regularly. We participate in large laboratory experiments. This is atmosphere simulation chambers. This one is a big one in Germany, and this one is in Spain. So where you simulate the chemistry that is happening in the atmosphere. And since I think 2 or 3 of us have actually a background in physics, we develop a lot of the instruments ourselves, which helps because I think we can develop very advanced instrumental techniques. Okay, so this is a technique what we are mostly using in my group. It is called proton transfer reaction mass spectrometry. It was developed back in Innsbruck from 20 years ago when I did my master's. And it's a very complex instrument, but the measurement principle is actually quite easy. So what we have is here, I should use this one here. So this is our inlet. So we suck in the air here through our inlet, and then we have this little reactor here at reduced pressure. And in here, the air that we analyze interact with these H3O plus ions. And what happens is then there is an ion molecule reaction, and the organic molecules, they get protonated. You just stick a proton on it, so it has a charge. And once your molecule is charged, you can analyze it in a mass spectrometer, which is nothing else than weighing it. Okay, so this is a 5 million crown scale. And so you are weighing the molecules very precisely or very accurately, and based on the weight, we can say what it is, or at least we can say the elemental composition. And the application is what we can do is, this analysis is very fast. You will see it in a minute. We can continuously monitor these volatile organic compounds. We can monitor aldehydes, ketones, alcohols, aromatic compounds, carboxylic acids, amines, all these kind of organic molecules. And here's one nice example of what you can do with such an instrument. You can put it on an aircraft, and this is data we gathered in the US. You probably have heard they have lots of problems with forest fires, and here this is actually taken from the front camera, and we fly over this is relatively small plumes, okay? And here you see the data that we collected and note that on the axis here. So we're talking about 10 seconds here. And so an aircraft flies very fast. We pass this first plume, the second plume, and you see the peak in benzene, toluene, and the higher aromatic compounds. Okay, it's a fast method. Of course, when you do ground-based measurements, you don't want to collect data at 10 Hertz. Then it's probably 1 minute time resolution is good enough. Then my group in Innsbruck, we have developed an additional tool, which we have named CARON, Chemical Analysis of Aerosol in real time or online. And because, if you go back, what we can measure, what we can analyze is gases. But what we do here is basically we sample the air through this device here, which is a honeycomb denuder. That means that the gases can diffuse to the walls and they are trapped by activated charcoal. So the gas, but the particles, as long as they are large enough, they make it through this denuder. And then we put it in this aerodynamic lens, which is nothing else than a stack of concentric lenses, where you basically concentrate the particle beam in the center here, and then we sample the particle beam into this tube, which is heated, and we evaporate the particles. And so we can then basically get rid of the gases in the what we have in the atmosphere, and then evaporate the particles and get the chemical composition of the particles online in real time. Okay, so we can measure PAHs in real time, polycyclic aliphatic hydrocarbons, anhydrous sugars, and so on. Okay, and these are exemplary PTRMS data of particles. So we get, there's lots of organic compounds, hundreds, if not thousands, in the particles, and this is bulk analysis. And so this is spectra we got in Lyon some years ago during winter time. So you see a lot of organic molecules. This is in Valencia in summertime, and this is in Innsbruck. And of course, this is very complex data, complex to interpret. But there is one nice tool which I have to introduce, is the so-called positive matrix factorization, or PMF, which is a multivariate statistical analysis of your data. It sounds complicated, but the underlying concept is relatively simple. Okay, so we start here on the left with the mass spectral matrix. So this is a mass spectrum we collect. And this is, one mass spectrum every minute, or every 10 seconds. So this is the time series. And the underlying assumption is that the mass spectrum that we collect in outdoor air is a linear combination of mass spectra that are generated by different sources. Okay, we know that wood burning has a certain fingerprint, a certain pattern. And traffic, the particles have a certain pattern. And then biogenic particles have a certain fingerprint, smoking has a certain fingerprint, and so on. Okay, so it's a combination of different sources. And then the variation, what you see in the real data, in the outdoor data, is a change when the different fractions from the different sources change. Okay, so that's a very powerful method, actually, and you will see this in a couple of minutes. And so, as I said, we usually measure in other places and very little in Norway. But we had the pandemic, so we had to do the measurements here. So the first thing is what we did is we stick the tube out of the window at the University of Oslo, but the chemistry department is not a very good place to measure chemicals. So we saw all the pollution from our chemists. So we decided, okay, that's not going to work. And then we tried to find something on campus, but let's say they were not very cooperative. And so I said, let's be provocative, go to the competitors. And so I have a good colleague, Peter Schultz at Oslo Metropolitan University. And so there's competition. I said, oh, of course you can come and measure. And so we gave us our lab, we installed it, and it's actually the location is even better because it's right downtown. So we have here the castle, Nationaltheatret, and it's Oslo Met here. So we could put it in his lab. And here you see the inlet. Okay, so this is where we sample the VOCs. So this is a long line taking it into the lab. It's heated. We have a small filter in here to protect the line and not to sample particles in there. And then we have another met station. This was actually installed by my colleague Massimo Cassiani from Nilo. Okay, so yeah, so we took our sample. We have another, you can see it here. We had also an NO2 monitor at some point. And this is just a side note. Actually, this is the filter that we changed periodically, like every month, to prevent the particles going into the instrument. So, okay, but it's still, you know, this is how Oslo Air looks like. So there's still things to do. But here's the table of VOCs that we actually found. Okay, I don't want to, you know, many of you are not chemists, so I don't want to bother you too much. But the main classes of compounds we found alcohols, ethanol, methanol, propanol. We found acetaldehyde, formaldehyde. Then the acids, acetic acid, carboxylic acid is acetic acid, formic acid, propionic acid. And yes, some aromatic compounds like benzene, toluene, C8 aromatics, C9 aromatics, okay? Now, I mean, you know, such kind of measurements have been done in many cities, but one very surprising finding was actually, you know, we had this very high ethanol concentrations. And we were struggling to explain because of, okay, one thing could be that the ethanol is actually in the fuel, but it didn't correlate with any of the traffic tracers. And then we noticed that it actually correlates very much with isopropanol, and to some extent with MEK. And then we, you know, this was the pandemic, and what did we use a lot, everybody of us? You know, antibac. Okay, so that was, I mean, a huge contribution from the antibac, and which is interesting because, you know, ethanol is a reactive compound, so it's a very nice finding. We should have published it, but, you know, I think we haven't had time yet. But no, this of course is not the real, you know, I mean, ideally, you know, this was only a time period where you have this ethanol. So we did not include the ethanol in the further analysis because if it would overwhelm just the whole source attribution thing. Is that because then it's like 50% of all your VOCs is due to antibac. You know, the message would be wrong. Okay, so we excluded the ethanol from the further analysis. Okay, and this is a time series. So we measured actually over 1 year. So that's nice. We have some time gaps where the instrument didn't work, but it worked out pretty well. And this is the time series for benzene. Okay, so benzene is emitted from traffic, we know, but also from wood burning. And here is the concentration in micrograms per cubic meters from, you know, December 2020 to December 2021. And you see that, you know, during the winter time, you have enhanced benzene concentrations. This has a variety of reasons. One of the reasons is, of course, the boundary layer is smaller, so, you know, you increase the levels, but you have also wood burning emissions and you have traffic emissions. And then, you know, it drops during the warmer season, but you see some increase here in the summertime. And then, again, an increase during winter time. And just to make the point here, the EU limit value for yearly average is 5 micrograms per cubic meter, so we're way below. So that's good, but still, you know, benzene is a carcinogen, so in principle, there is no lower threshold. Yes, so, but benzene is not a very specific tracer compounds because it has multiple sources. We have other compounds like this one here, furfural. This is very specific for wood burning. Okay, this compound is emitted, and that's a nice thing about PTRMS. You know, we have a series of molecules that are very specific for different sources, and so we can then apportion the sources, quantify the different sources. And you clearly see here that, you know, the furfural, okay, dominates in the wintertime when you have, you know, a couple of micrograms per cubic meter, very low emissions during the summertime. I mean, here you see a little bit, you know, August, September. That's when you have also the wood burning and grilling when you emission, and then again very strong during winter. Okay, so this is the time series of furfural, and then I will go through the results from the source apportionment or PMF analysis. And if you're not used to it, it's a bit complicated, so I will spend some time on this. Okay, so on the x-axis you have the date, the month, and here is the factor contribution in micrograms per cubic meter. So how much the specific source contributes to the total VOC load. Okay, so the total VOC load here varies, from like maybe 15 to 35 micrograms. And what you see here is, let's first look on the relative contributions. So here is in blue is the traffic one. Okay, so traffic is about 10 micrograms, a little bit less during the summer. You clearly see that in July, I mean, everybody's gone, so we have a very low contribution from traffic. You see that here in the how do you call it, brownish thing is the wood burning. The wood burning is only visible, or a strong contribution only during the winter periods. And interestingly, wood burning here, for example, in January exceeds actually the contribution from traffic. Okay. And then we have, what else do we note here? So in green is the biogenic. So there's not a lot of isoprene emitters in Oslo, so the biogenic contribution is relatively small, but you see in July and August, you see the contribution from biogenic volatile organic compounds. And then what we also, I mean, we called it grilling. It is, we see the wood burning tracer, but it has a different fingerprint. And we only see it appearing in summer. Okay, so that's why we call it the grilling, and then you see the main contribution here comes in the months of August and September. Okay, so this is a first output from the PMF analysis, and this is a standard program that we're using, and there's actually a Baptiste here in the audience who did this analysis. So thank you. And so the output here is also what. Additional outputs, what you can get is how the average weekly cycle looks like, how the average daily cycle looks like, how the contribution looks over the month and over the day. And I think this is very informative. And note that here on the y-axis, everything is basically scaled or averaged to 1. So to see the relative changes over the course of the day. Okay, so you clearly see here. If you let's start with the average diurnal cycle over 1 year. So we see here this comes from the wood burning. So I should use this one here. Okay, so wood burning clearly in the evening we see. I mean, that makes sense. You have the higher emissions when the people fire up their fireplaces in the evening. It's during the night, and then it drops during the day. So this is the average diurnal cycle. You see. In blue, the traffic. So you see the morning rush hour, then the drop during the day, and then the more smeared out afternoon rush hour, and then the drop. Now, this may surprise you that you have higher biogenic emissions during the night, but this is something we have seen in many other places, because these are actually not isoprene emissions. This is not the VOCs that are emitted when light shines on the plants. It's more like temperature, and the wind during summertime, the temperature in night is also high, and so this is monoterpenes basically, for those of you who know. And we know that Oslo is made that that the flow pattern is during the day we have the air coming from the sea moving up, and then at night the air is coming from the forests down into the city, and so that's what we actually see here. Okay, so this is monoterpenes coming into the city from the forest to the north. Okay, and then what else? What we can highlight here? So do you see this is from the average diurnal cycle. What you also see here, you can see weekday, weekend effects. So you nicely see it. For example, here in the traffic, you see the in blue. You see the 2 rush hour peaks, and the rush hour peaks disappearing on Saturday and Sunday. And yes, what else did I see? So what I noticed here is, for example, if you look at the contribution here on a monthly mean, so you see that you have a very strong contribution of the wood burning during the January and February months. You see the biogenic contribution peaking in green here, peaking in the summer months. What is interesting is also this. That's why we actually noticed we saw this second biomass burning factor that actually peaked in the summer, and that is the only explanation we have is that you can have this grilling. Okay, so and then we have the aged means photochemically processed. So the air pollution stays in the air. It gets oxidized by ozone and OH. It stays, it's old processed air. And that's again, the photochemical activity is higher during summer. That's why it peaks during the summer months. And if you want, so even the wood burning here, for example, you see it typically more higher on the Saturday and Sunday. So I think this shows, it's a very powerful method. We were very, very pleased to see these results. And that's actually, we Baptiste produced them 2 days ago. So that's always a good incentive to go to a conference, because then you actually have to process the data. Okay, so, and then what is also interesting, this is another output, and this is probably too much chemistry, but I'll just highlight a few things here. So this is the list of compounds we detected in the air. And then you can say, you can look at, if you have, for example, benzene, what is the source of your benzene in the air, okay? And then what we see here is, if you have benzene, so like 50% or maybe 40 to 50% of your benzene actually comes from the traffic source, but a significant contribution comes from the wood burning. And that we know, the wood burning. So it's not only the traffic that emits the benzene, while we know for other compounds like toluene, C9, and C10 aromatics, we know that the emissions are relatively low for the wood burning, so that these are dominated by the traffic emissions. And then we see some other compounds, like here, the formaldehyde and methanol. These are oxygenated compounds. This we know they are photochemically formed. And yes, one other. What else do we have here in interest? So, for example, the furan. This is one of our biomass burning tracers. So, bifuran and furfural is examples of where this furfural, you see it's entirely in the wood burning. Okay, so you can also look at the sources for the individual compounds, and some of them may be interesting, like the benzene, because you probably want to know what makes a benzene acidity. So I think that's that is what I have to show about the measurements in Oslo. And let me see how I'm doing time. Yes, so that's still good. So this is the measurements we actually did in Innsbruck, and that was a couple of years ago. And as I mentioned, we can also measure particles with this Karen inlet. And so this is when we did some measurements in the early winter in Innsbruck. And this is this was published in Analytical Chemistry. And so this is the mass spectrum, how it looks like. These are, for example, some tracers of, this is a PAH, and this is levoglucosan, is a biomass burning tracer. But again, we go to the next slide here. We again did the source apportionment. And we again found a very strong contribution from biomass burning, and we found this biomass burning in several factors, which means that it can be originated biomass burning, but it can have different sources and different processing. So the variability cannot explained by a single factor. Okay. So for example, again, so even in the particles, for example, you can apportion the sources. You can quantify the sources for the different particles. So, for example, you see here in green the traffic factor. You see the morning peak and the afternoon peak. You see the biomass burning peaks that have a different time evolution. Interestingly, those of you who have been to Austria, you know that people smoke a lot in Austria. And this is actually on a university campus. And so we saw a strong contribution from the cigarette smoking. And if you look at the mass, we can look at what actually is it that makes us in the mass spectrum in this factor that tells us this comes from cigarette smoking. So this peak here is nicotine. And this one is actually interesting. This is the mass THC. So those of you know, so cannabis. So this is on a university campus. So, okay, so again, it's and so this is what we can do. We did this for 1 week of measurements in Innsbruck. Of course, the ambition would be to do this for 1 year in Oslo. The problem being that that takes a lot of time to run the instrument, to babysit the instrument, to make it sure it's calibrated, and to analyze the data. And yes, I think this is also, so PAHs is of course an important issue. And so we looked, well, sorry, first I start with the contribution from biomass burning organic aerosol and from primary organic aerosol from traffic. The contribution, and you see here, this is in micrograms per cubic meter. So this is what you see here, where we are varying between 1 and 2, and here the traffic is way below. Okay, so like 5 to 10. Okay, so the message here is, at least the organic particles in Innsbruck during the heating season is mostly caused by biomass burning, not by traffic. And I guess the same probably holds for Oslo. And then you can look at the PAHs. So we look at the different PAHs. What is the source of the PAHs in the particles? And the same message: 2/3, 3/4 from biomass burning, and only 1/4 from traffic. Okay. So and then.
Sorry, Armin.
Yes.
Would you like to have a question during your presentation or at the end?
At the end.
At the end. Okay.
How much time do you have?
You got enough time. That's no problem.
Okay, and then just, this was a lot of chemistry and complexity. Now I just show, some things we do for fun. So we couldn't, this was during the pandemics, and we decided, okay, there is now these, new Euro 6 cars. We'd have these fancy SCR devices. So we said, okay, let's put the mass pack on the car with a big battery pack, and sample from the exhaust and do emission measurements. And I'm not going to show the day. I'm just showing that we are actually able to do such onboard emission measurements. And so basically we have our instrument sitting in the back of the car, and then here you have an exhaust flow meter. And I'm going to show. So here we're driving. Some of you may know this place. So what I show here is a movie. So this is the mass spectrum we get with the full mass spectrum of emissions. And down here you see the time traces of benzene, toluene, xylene, and 3-methylbenzenes. Let's see if I can start this. Obviously not. Okay, so you see, again here we're recording at high time resolution the emissions of benzene, toluene, and the other compounds. So we can basically determine on-road emission factors for the latest Euro 6 cars, and this is actually work in progress, and I hope we can publish it this year. And we found some unknown emissions, so that's unknown compounds being emitted. So that's going to be interesting. And you see there's a high variability. Okay, and then since when I saw the agenda, there's lots of talks about microplastics, and Nikos from Nilu, he actually invited me to participate in his project here, Airborne Microplastic Detection, Origin, Transport, and Global, which is supposed to start soon. It has not started yet, funded by Research Council, 3 years. And I've explained to you that we are measurement expert, and I'm quite confident that we will be able to detect micro and nanoplastics in the air. We have seen that a lot of the large fraction is actually in the sub-micrometer regime. So the ambition or the goal, at least from our side, is to adapt our method to detect microplastic and quantify microplastic in the PM1. That's what we're going to try, and we're going to start probably in autumn. So maybe in 2 years, I have something to show, hopefully. And then some suggestions for future work. This is something I wanted to do for a long time. I wanted to convince my master students, but so far I have not been succeeded. This is something really, something that should be looked at, right? If you go in the summer, I know that people love these kind of tools, but they should be forbidden. That's and maybe if we have some data, there is a reason to do so, right? So you should should do this. And the other thing is, I think there's a lot of focus on ship emissions, but from the large ships. But if you go in summertime, actually you can smell. Over the fjord, you can smell the onboard hydrocarbons from the outboarder engines. And so I think I think that's something you should look as well. Should be looked at as well. Okay, it's a short period, and probably on the yearly average, it doesn't matter too much. But I think I'm pretty sure that this summer that you will see the summertime pollution episodes caused by these sources. So that's my suggestion to look after this. I think that's all I have to say. Thank you.
Thank you, Armin. There is at least one question in the chat. We could start there, and then there is 2, 3 in the room.
Yes. Do you hear me? Hello? Yes.
Yeah.
Hanne Veggeberg asks, what are the sources for the chemical fingerprints for the various source types used for the PMF?
Say again?
What are the sources for the chemical fingerprints for the various source types used for PMF?
The sources for the various chemical fingerprints. Okay, so basically what we record is the mass spectra. Okay, so we sample air and we record a full mass spectrum that has all these compounds in there. Okay, so these are the different compounds we measure. We put this as an input, and then you know that basically you have to explain the variability you see with a linear combination of different factors that have these various amounts of these compounds in there. Okay, so then you see it better, for example, in the Innsbruck experiment. That's what the outcome then have. You have a full mass spectrum, and then you know the multivariate statistical method identifies the various factors, but the factor alone doesn't tell you. Now this is just a statistical output, but then we have the mass each factor is associated with a mass spectrum. Okay, and then we can say, okay, this is the mass spectrum, and then we look at the peaks and they say, okay, this is nicotine, this is THC, okay, this is a smoking, and then here, for example, biomass burning, this is levoglucosan, which we perfectly know that this is mainly emitted. Okay, so the chemical information comes from the mass spectrum, which we are able to then assign to certain tracers. So.
Espen from the Public Health Institute. I just wonder if you can increase the resolution of the traffic emission, for example, to distinguish between diesel or gasoline or emission from ship from the harbors.
So we would need to, I mean, that's that's challenging, yes. I think we have to look at if there are specific tracers for diesel and gasoline. I think one possibility could be the ethanol, because the ethanol is only in the gasoline, right? My understanding, it's E90, so you have 5% ethanol in the gasoline. But I mean, here we have the confounding factor from the antibac. So in principle, yes, but I don't think in this data set it will be possible. And then for the ship, I think it will be rare that we have these, at least where we measured, that we have all the pollution coming all the way to the sampling location where we were. But probably if you sample in the harbor, I think you would probably see more clear the signature from the port. I don't think, from all kind of shipping activities.
Okay. Bruce Denby from Meteorological Institute. Very interesting. I want to get this data. Thank you very much. Could you go back to where you showed the sort of monthly source attribution? One more. Yeah, here. Factor contribution. Could you just explain that again? Because it's in micrograms per meter cubed. There are not 30 micrograms per meter cubed of VOC in the air.
Yes, it's not PM, it's VOCs.
So it is VOCs?
VOCs, yes.
Okay. So this is the actual concentration of all.
This is the actual concentration, yes. But it's the VOCs. I mean, so the Innsbruck thing is particles, but the one in Oslo, we measured gases.
Okay, good. Thank you.
We have another question from Torleif Veidal. did you see any signature of evaporation emissions from fuel tanks or from nearby gas filling stations?
That's a good point. As I said, we processed this a couple of days ago, so I think that we should look for the evaporative emissions. I mean, there was no. I don't think there's a nearby gas fueling station, but we did some similar measurements actually in Austria, and we have clearly seen the evaporative emissions. And there's an easy way to diagnose those. Okay, so because we can look at the benzene to toluene ratio and the higher alkyl, and so they have all higher boiling points. The higher you go in the if you have a C6, C7, C8, C9, C10, we have this whole series of aromatics that come from traffic. But then the boiling point increases, so the ratio changes with temperature, the emission ratio. And so there is an easy way to, if we plot this, we have the temperature data. If we plot the ratio, for example, toluene to benzene versus temperature, we could get the number on how much comes from evaporative emissions. So that's a different, because the variability would, I don't see, because this PMF works on the variability. I don't think it would affect you would see it in the variability, on the fluctuations, but you would see it in the ratios between the different traffic markers.
Hi, Susanna from Nilo. My question is similar to the one of Espen, but focusing on wood burning. Is it possible, in the same way that we see that, for example, with particles, you have a different profile for size distribution if it's fresh from wood burning or if it is aged? Is it possible with this technique, for example, the wood burning in Oslo, to see how much is local contribution and how much is from the surrounded municipalities?
Yes, I think that would, because there's some, actually, where is it? It's here. So there, if we see those, there is, because what you see here, this succinic anhydride, this comes from wood burning, but it's actually not a direct emission. It's an oxidation product. So what we'll be able to distinguish is fresh wood burning emission and aged. Okay, but aged could be also local circulation in Oslo. So you cannot blame the neighbors. So that's I think what can be done easily between fresh emissions and aged, and that's what we actually saw also. I mean, we didn't go into detail, but I think some of these different biomass burning factors is because some of them are fresh and some, at least one of them is fresh and one is aged. But then you would have to look if there is another tracer when the wind comes from that area. So you would probably also want to include more information like the wind direction and wind speed, so to blame the surrounding neighborhoods.
I saw that you started the measurement in December 2020. It's a pity that you didn't start it earlier, because in 2021 we have a very special situation. In September is when we had the very strong increase in electricity price. So it would be great to see your result in a year previous when the electricity price was more normal. It's a pity that you don't have 2 years getting this special situation.
We have some data earlier, but that's at the chemistry department. So maybe we can get some. But I mean, the acetonitrile, that's the biomass burning, and that's it's a solvent. I mean, that was huge. So I don't think you can use those data. But we also wanted, because you could have seen it also I think this winter, probably people are using more. I'm pretty convinced. But yes, but this was all unfunded, so we cannot run a 3-year campaign without any funding, even if you're at the university.
Yeah. I see that you are the only one who had fun during COVID-19.
Any more question to Armin Visthaler?
I'll be here for lunch, so if people have questions, they can ask.
Then you will also have this small gift from the road administration. It's written in Norwegian, so you could look at the picture. I think the picture is actually the most interesting, and you can use it to learn some Norwegian. Thank you very much for your presentation.